Welcome to the talk on OCI architecture, a peek under the hood. Well, I'm going to essentially talk about some of the key architectural aspects of OCI, cloud that has actually enabled us to differentiate really well from our competitors. My name is Pradeep Vincent. I'm a senior vice president in OCI. I've been with OCI pretty much from the beginning, 8 years now, and I've worked on many different aspects of OCI architecture. First, I'll start off with OCI journey itself. So we started off, I joined 2014, and we launched our first region, which is really the first launch of our cloud in 2016. We first launched our first region in Phoenix, and then next couple of years we actually expanded pretty quickly to IID, LHR, FRA, which is like 4 big regions in Virginia region and London and Germany. Now, while we did all this in the first couple of years, actually it's really 1.5 years, we also talked to our customers. And what we wanted to find out was, what are some of the core challenges customers are facing that nobody else solves, or really no hyperscaler cloud provider is actually solving, so that we really wanted to focus on that. So we've been talking, as part of the conversation, we found out 2 big buckets of challenges that customers face that nobody was really trying to solve. The first one is a broad category around data residency, sovereignty, data privacy, jurisdiction, and compliance. Fundamentally, what this boils down to is the world is becoming fragmented, and data and compute are increasingly becoming critical utilities that every government entity and governance entity cares about. Every country cares about it. Every geo area cares about it. They want to have more control, or how the data that's collected in that country is handled. They want more control in terms of who can actually shut down the compute that they rely on, right? And it's fundamentally becoming no different than water or power, if you will, right? It's so important, so critical, and it's actually going in that direction. And in many cases, if you look at the hyperscalers, well, so the general strategy is, hey, let's actually build really large regions, and then all the customers, please come on over here and use our cloud. And that doesn't quite align with this whole thing around data residency and sovereignty that's actually generating requirements that are local in nature, country local in nature, with compliance requirements that are country local in nature. And this is a fundamental challenge that we find that, like many of our customers, we're facing as we are contemplating move from on-prem to the cloud. The second category of challenge was essentially around multi-cloud. And it's really around vendor lock-in and how do you actually safely migrate. Fundamentally, customers want to have multiple bets. They want to have multiple clouds. They want to use different services that are best in breed in different clouds, without essentially feeling like they are locked into exactly one cloud. We took these 2 big categories of feedback, and we essentially came up with product strategy that actually solve these 2. First, we actually started launching many smaller regions, including DRCC, or Cloud Customer Private Regions. And we also started launching many small regions across the world. There are public regions as well. So we have both private and public regions. And this is in addition to large public regions that we have, right? Like an IID region or Phoenix or LHR FRA, they're fairly big, but in addition to that, we also have a lot of other regions, and we also have private regions. And as you can see, we already launched 40 public regions and growing really, really, really fast, right? And this is discounting all the private regions, which I'm not showing in the map, and this is discounting some of the government-related regions as well. So essentially, in the last, if you look at the last few years, the number of regions that we have launched is really grown quite a bit. In addition to that, in order to enable customers to use multiple clouds, we essentially took a two-pronged strategy. First, we essentially wanted to invest and launch product offerings that fundamentally offer seamless customer experience when they're on multiple clouds. Let's say an Azure and OCI. We want to offer those customers fundamentally seamless experience so that use services but from both sides. Second, we align with established industry standards such as Kafka or Kubernetes or L2 networking. These are all protocols and standards in different parts of OCI platform, that where we have chosen to align with existing standards and traditional standards, if you will, so that it's much easier for customers to, one, migrate from on-prem to OCI, and two, perhaps use multiple clouds or on-prem and OCI as well, right? So fundamentally, we took a two-pronged approach. Now, in order to achieve all of this, we had to step back and pivot our core architecture to solve these customer problems, right? And that's really what this talk is all about. First, let's actually take a look at the architectural changes, our architecture enhancements that we've been investing in to handle a variety of region sizes, right? Not just scaled up really big regions, right? But also small size regions, which actually brings in a unique set of challenges. The first, big investment area is essentially about how do we actually shrink the region launch footprint so that when we launch a region, it's actually fairly small, right? And also provides the foundational building blocks so that we can actually scale the region as there's more customers, as there's more traffic, there's more demand, right? So it's not about launching a small region that stays small. This is really about launching a small region, but actually growing that along with the demand, right? And we came up with a variety of techniques at the engineering level to actually deal with smaller region sizes as well as large region sizes. Now, the first technique that we came up with was essentially the observation that sometimes we need different algorithms or perhaps different configurations of the same algorithm based on the scale. Cost optimizations that are designed for very high scale, right, and that leverage very high scale in order to bring down costs can sometimes be counterproductive in small regions. And as a result, we kind of need to differentiate our strategy based on the size of the region. A very good example of this is erasure coding for replication. So let me actually start with what erasure coding is. Erasure coding is a very popular technique used for achieving high durability in storage subsystems, and and it actually can do that while really lowering the cost, particularly at scale. A very quick run through of what this looks like. So this is a rough high level example. We have a input phrase: Jack and Jill went up the hill to fetch a pail of water, and it has some number of bytes. That phrase, or the payload, if you will, goes into a erasure coding encoder, if you will, that has a specific parameter and type. And in this case, it's N and K. N is essentially the number of shards that are pieces of storage units that the encoder actually spits out. In this particular case, N is 6, so it actually spits out 6 shards, as you can see in the center, right? And K is essentially the minimum number of shards the decoder on the right side needs in order to reconstruct the original payload back. The fundamental aspect here is that imagine this is a storage subsystem. We take the 6 shards and actually spread the 6 shards across a whole bunch of different nodes, or maybe even different racks or different data centers. What that means is that I can afford to lose 1 or 2 shards, and still I should be able to reconstruct, the original payload. And that fundamentally is the, concept behind durability, right? And as we increase, as we increase EN, we can actually decrease the ratio between N and K, which is actually, I'm calling it a stretch factor. The stretch factor is essentially the amount of storage that is required on the physical disk drives, whether it's hard drives or NVMe, to store 1 byte of actual payload. Imagine the payload is 1,000 bytes. In this particular case, the stretch factor is n divided by k, which is 1.5. As a result, in order to store 1,000 bytes of actual, end customer payload, we need to have 1,500 bytes on the NVMe or the hard drives. That is essentially the stretch factor. Now, the lower the stretch factor, better it is from a cost perspective. But low stretch factor also means the I/O bandwidth requirements goes up, and a larger fleet size is also required in order to achieve a specific durability goal. And this is a very, very important aspect. So fundamentally, with scale, we can actually reduce the stretch factor, and it actually delivers us, increased cost saving. On the other hand, high stretch factor is really good in order to achieve durability or a particular durability goal with a much smaller fleet size. But at scale, it's not as cost effective. At small scale, it doesn't matter. It's okay. It's not a big deal. But when you start to scale, it becomes less cost effective. So one of the things, we do is, depending on the size of the region, right, or the size of the cluster that we use in the storage system, we actually vary the stretch factor based on the region size, right? This is just one of the examples by which we vary the algorithm or the configuration of the algorithm in order to, be effective with small regions as well as large regions. The next technique that we use is essentially, managing specialization of the hardware. What does that mean? First of all, why specialized hardware? Specializing hardware means we essentially look at every single workload and figure out what is the most appropriate hardware for that is, and then investing or essentially building a fleet of that hardware in order to serve that workload. The reality is that there are tons and tons of workloads, and they all have their own variances. But at scale, in order to be most cost effective, we essentially have a bunch of buckets of workloads for which we have specialized hardware for. And the specialized hardware could be in the form of, different, CPU to memory ratio, different types of, hard drives or NVMEs that has different cost and I/O performance characteristics that may be appropriate for that particular workload, right? Now, the challenge with, having a lot of different hardware types is that the initial cost when you actually build a small region can actually be high. So what we do is we actually, want to manage this carefully, particularly when you have smaller regions. So with smaller regions, our fundamental strategy is to have less specialized hardware so that the initial footprint or the fixed cost of the region is actually lower. And then as we grow, as the region grows, we have more specialized hardware. As an example, when we have a storage subsystem, so we have block, we have object, right? Below that, we actually can have, underlying fleet that consists of hard drives or NVMe. And in fact, we could actually have different types of hardware, hard drives, or different types of NVMEs based on the price and the IOPS characteristics as well. Now, the observation here and the way we leverage this is, so in a small, region, we can essentially take an NVMe subsystem and actually make that serve not just block or object, right? So now object store, even though, at scale, it really needs to be built on a hard drive platform that is a lot more cost effective from a, dollar per terabyte, perspective. But in a small region, it may be okay to actually start out with the NVMe storage. And then as we grow, scale the region, we add more types of, underlying storage subsystem. And then we essentially change the block storage and object store front end to use different types of underlying storage subsystems, right? So fundamentally what this boils down to is we kind of need to, abstract the front end interface a bit and essentially have block storage and object store somewhat be agnostic of the underlying subsystem so that we can change that on the fly. Another example of this is essentially network gateway fleet. Now, network gateway, what is it? Well, it's essentially a set of servers that essentially specialize in processing packets, right? That go out of the data center into the data center or one part of the data center another, so on and so forth. And this fleet, it's not just passing packets just for fun. They actually implement a set of functions. The functions may be internet connectivity, it may be virtual networking peering, it may be fast connect peering, or it may be network load balancer. So there's a variety of functions that are implemented on these network gateway fleet. Now, typically, when you have scale, we actually want to have multiple instantiations of this fleet so that we can, optimize for bandwidth management. As an example, when you have a large region, we probably have like multiple points of presence where, what that points of presence is essentially a specialized a set of racks that are actually placed much closer to a peering site in order to optimize for peering relationship with network providers. So our data centers are in like a much larger space, and then there's network cables that go out of that into points of presence locations that may be slightly away from the data center, but then much closer so that we can physically peer with like some other network peering provider. On the other hand, there are other types of traffic that are entirely within our data center, such as virtual network peering, where one private network inside OCI peers with another private network inside OCI. We essentially want to have network gateway fleet at different locations. In this particular case, some of them in the POP locations, and some of them inside our core network itself, so that they can handle different types of network functions. That's all great, but then when you have actually a smaller region, there may be less of a justification, if you will, or less of a scale to actually justify multiple fleets. And it may be much better, easier, and more efficient, and actually more available in many cases, to have a consolidated network gateway fleet. So what we do is essentially start with a consolidated fleet that does all kinds of functions. And then as we grow the region, we essentially have multiple gateway fleets, and they have differentiated functionality, if you will. The third technique that we use is essentially variable deployment and operational configurations. Well, what does that mean? So operational configuration essentially is around, let's say it's about capacity and alarming. Those two are good examples of it. There are many different types of operational configurations, but I'm just picking a couple of examples to drive home the point. In small regions, there's generally more variability in load patterns. The peak to average load tends to be higher. What that means is that in a smaller region, if you look at a service load, it may be really, really low, and then suddenly it could really pick up as customers, turn up the traffic, right? And in a large region, well, same thing happens, except there are a lot more customers, a lot more traffic. So, the traffic overall load tends to be more smoother. This has some implications. In smaller region, if you look at it per service or sub-service level, the capacity ramp up and ramp down needs to be more aggressive. What that means is that we may start with very small amount of capacity for our service. But then the moment we see, the traffic ramping up, we need to quickly add capacity to that service, right? So we need to have an appropriate strategy for that. And alarming, similarly, there's going to be more variance. As an example, in a large region, we might actually alarm for an expected band of traffic. Let's say in object store, we expect that the overall traffic is going to be between X and Y. We might actually set an alarm saying that, hey, if the traffic load drops below X, alarm, right? Why? Because it's probably some bug or error or something gone wrong in the system, why the traffic or the load has dropped, right? We kind of infer the traffic load drop as some challenge with the region. On the other hand, small regions tend to have more variance, which means that, well, it's, the band, if you will, of acceptable range tends to be higher. So we need to have alarming configurations that are appropriate for that, right? So, and similarly for deployment. So in a deployment, when you have a large scale, you can actually leverage the scale to slow roll changes safely. As an example, we can deploy 10%. Let's say there's a fleet of nodes, and let's say there are 100 nodes. You can essentially deploy to 10 of those nodes, pause, check for anomalies, wait for all the canaries to kick in, and verify if that deployment has actually succeeded. And then finally proceed to the next 10%, and then keep going, rinse and repeat, rinse and repeat. And that's a pretty popular way to deploy safely, particularly in large regions. Now, in smaller regions, depending on the type of service, sometimes the size of the fleet may not be that big. And as a result, taking down 10% and deploying new code may not give you the same verification or safety that you want. So instead, we may actually want to have a different technique where we, instead of taking 10% of the existing fleet, we may actually want to increase the fleet size temporarily during the deployment process. Let's say add 25% more capacity, and then deploy through that 25%. Check for anomalies, just like as you do. Check for your canaries, and then rinse and repeat. And then finally, once you're done with the deployment, release the 25%, right? Note that if every service wants to deploy at the same time, we are not going to have the additional 25% capacity might actually become a challenge. But we can essentially do something like this as long as the deployments are not happening exactly at the same time, right? So fundamentally, what this boils down to is that at scale we can leverage the scale for a variety of things. But when you have a smaller scale, we kind of need to come up with appropriate techniques so that we can have similar availability, but yet do all that with a smaller fleet size. The fourth technique is essentially, how we fundamentally build our networking and data center expansion. So when we started out with like, hey, we're going to have, big network. It has, racks, and it has, the racks all connect to a next level of switches, which then connect to next level of switches, and then you have a spine and maybe a super spine for large regions, so on and so forth. But instead of that, we essentially, came up with the architecture that essentially has a modular approach. What that means is like it has a smaller, initial footprint from a networking perspective, right? And we actually shrunk our network footprint by more than 70% this way. But then we actually designed a rack and network architecture to allow scaling in small increments. So it's not that we have to land the entire spine in one shot, but we can actually land appropriate switches at every level in order to expand in modules, right? And that's actually quite important when we actually want to launch a small region and grow the region over time. Similarly, let's say we actually, particularly for private regions, sometimes, well, you actually start with the data center space, but there's no data center space available in literally the same building. Well, maybe actually go, get some more power and space from the next building, and then we kind of need to connect them. So we actually also have a modular approach where we can actually connect parent site and child sites, and we already have talked through from an architecture standpoint how you do that. And we essentially, WDM is wavelength division multiplexing, which is a common technology used for connecting different data centers with a high performance, low latency network fabric. And we essentially leverage that, and we have an architecture that allows us to expand in a modular fashion. The fifth technique that we use is essentially around, well, so if you think about particularly private regions, where we actually launch our regions inside customers' data center. In many cases, customers actually want to have a region in a single data center, right? Because a variety of limitations. And we actually want to enable customers to build high availability applications or services even within a single data center. We actually came up with a construct called fault domains in order to help customers do that. And we also leveraged the same construct internally for our purposes. A fault domain, at the end of the day, is a grouping of hardware and infrastructure that provides anti-affinity and failure isolation within a single data center or AD, right? So if you look at what's inside a fault domain, well, it's essentially a bunch of racks and the switches associated with that and rack PDUs. So essentially, it provides rack level power and data center isolation. And in addition to that, the software stack associated with each FD, whether it's like the hypervisors that go into each one of the servers or whatever else there may be, they're all fully isolated, right? And with the fault domain, we can essentially empower customers to build high availability applications. This does not look any different than any other replication mechanism. So it's like we have 3 fault domains, and each fault domain has a set of resources, compute resources or whatnot. And customers launch compute resources in different fault domains, and then set up replication and failure across them. And in fact, our services internally, including a block storage, an object store, and database services, leverage the same constructs internally. So with fault domains, what we have done is we have taken what we internally use and exposed it to the external customers, so that as customers, you can also build using the same constructs. And then for maximum resiliency, in fact, I have another CloudWorld talk that actually talks about why we fundamentally believe the maximum resiliency. In order to achieve maximum resiliency, you actually need to have multiple regions, right? That is a fundamental belief, and it's our recommendation that customers for mission critical applications, you actually have multiple regions, and within a region, you essentially use fault domains to achieve high availability. And one of the key advantages of this model is that within a data center, our network is extremely high bandwidth and low latency. So it actually allows us to build clusters that are really high performance. And in fact, many of our OCI services essentially use the same mechanism. So the architecture for small regions is fundamentally different in a variety of ways. Your replication algorithms are different, hardware fleet optimization different, so on and so forth. Well, this leads us to a core architectural choice, which boils down to, should we have dual stack or a single stack for small regions and large regions, right? And there are pros and cons to that, so it's not an easy or obvious answer. So if you look at it, if you have a single stack, you have like a single code base build, but then you kind of deploy to small and large regions, and you kind of have a single operational model that cuts across all of them. And with dual stack, you essentially have a separate code base and deployment model and so on and so forth. Now, if you look at these differences that I just talked about, they might actually point to a dual stack approach. Well, we can actually separate everything easily. So that seems like a natural fit. But on the other hand, we actually ended up picking the single stack approach. Why is that? Well, it actually starts from our product goals. When we do small regions, whether it's public region or private region, our fundamental goal is to have independent region. The regions should not be attached to a mothership region, if you will, for control plane or data plane or for any of the service. They are fully independent, right? And then in addition to that, we want to have all OCI services in all regions. So it's not like a select subset of core services, it's like all services, right? And this is important because if you think about how applications are built in cloud environment, it's really a platform. It's not a service, it's not a product, it's actually a platform where when you build an application on a cloud platform, you kind of want to rely on all the services in that platform. And when you actually have a platform where the number of services or what services available and it varies by region, well, it's really hard to actually build an application, right? So we fundamentally want to have all services in all regions. And then we want to start the region small and grow big. So it's not like small and big regions are like two different paths. They are, we're going to start small, but then many regions, we expect them to grow big over time. And we want to support that as well. And then last but not the least, we want to deliver fast-paced innovation in all regions. I'll get to that in a minute. Now, with dual stacks, one of the core challenges is that it kind of means double the engineering cost. Not quite double, probably a little less than double, but still is substantially higher than having a single stack. Now, typically what that means is that if you choose a dual stack approach, the evolution from small to large is obviously very, very hard, because when you have a small region, you use one code base, and at some point you kind of need to rip that off and then put the new code base in, which is really hard and almost impossible. So can't really do that. All that you can do is essentially tell customers, no, you gotta like abandon your small region and go to the other region. In addition, when you have dual, code base or stacks, well, you really want to, minimize the engineering overhead. So it's almost going to be tempting to use, minimize the amount of functionality in the small private regions. And last but not the least, it's also going to be very tempting to say, hey, why can't you actually use the functionality in this other region and just like tether that to the mothership region, if you will, and have a small local zones or whatnot. So fundamentally, the dual stack approach forces a bunch of undesirable trade-offs that conflicts with our product goals. And that's why we ended up selecting single stack approach, because it actually allows us to start small and grow big, allows us to have all the services in all regions, and have independent regions. But that still leaves a question: how are you going to handle all these differences while also having a single stack? So one of the things we had to do was step back and look at the services. In many cases, we kind of had to refactor some of our services or the platforms on which those services are built on. So we kind of have a common code base for that applicable generally, and then we also have specific algorithms or subcomponents that are applicable to small regions or large regions. And we also had to architect in such a way wherein we can flip from one component to another on the fly, so that when the region grows from small region to large region, they can essentially organically grow without actually having to rip things apart. Right? Similarly, for operation practices, we kind of want to have the same operational model, but then like there's a bunch of aspects such as alarming configuration, whatnot, they're actually going to be different. So we essentially took a different approach. We have single model, but then a bunch of aspects are different. Last but not the least, why do we actually have a single stack? Well, it's because we want to deliver on the fast innovation iteration. Cloud is synonymous with fast innovation iteration. What enables fast innovation iteration in the cloud? Well, cloud does not have a version. Cloud does not have a version. Well, what does it mean? So if you look at on-prem products, most of them have some form of version. Well, version 11.1, or we're going to do a big upgrade from version 12 to version 13, and so on and so forth. There's a lot of conversation about version. But if you look at cloud, if you look at any cloud product, there is no version to the cloud itself. Well, how do we actually achieve it? Well, one, we actually have inside the cloud, there are many different components. Across these components, we have very strong APIs and SLAs. So it's almost like a bunch of independent services that can be deployed independently, right? And because of this, we can actually afford to have independent, uncoordinated deployments across all these services. As an example, well, in this example, I've depicted virtual networking, block, and compute. Those are three big core services in OCI. These three services essentially have strong APIs and SLAs across them. And they have independent deployment trains. And as a result, there's no one point where the exact version of compute and block and networking match up. But that's okay because of the strong SLAs and APIs where we actually take into account backward compatibility and so on and so forth. What this boils down to is that the engineering teams working in virtual networking now don't have to worry about coordinating every single thing with block storage. And block storage engineering teams don't have to coordinate with compute and so on and so forth. And this actually fundamentally increases velocity. And that's actually one of the reasons the agility and the innovations are much higher in cloud environment. We have that advantage with large regions, and we want to preserve that advantage with small regions. And that's one of the reasons we want to have a single unified stack and deployment model, so that we preserve the same cloud agility and pace of innovation for small regions, private regions, large regions, and public regions. Everything the same, right? Next, let's actually take a look, at architectural aspects of multi-cloud environment, or more importantly, multi-cloud strategy for OCI. Well, what is multi-cloud? Well, it's actually fairly simple. Well, you actually, let's say I'm a customer. I want to use Azure and I want to use OCI, and I want to be able to use both of them in a seamless fashion. Now, industry actually refers to multi-cloud to mean many different things and many different types of combinations. In OCI, we actually have a more opinionated strategy, if you will, where we want to deliver a more seamless customer experience. What does it mean? Let's actually take an example of a product that we actually launched recently, Oracle Database Service for Azure. Now, if you look at this, this is like a launch screen. It kind of has the skin of a Azure launch mechanism, except that the parameters are actually relevant to OCI database service. So when you actually launch the Oracle Database Service for Azure, the database itself actually lives inside OCI. But what we do is we abstract away the differences between the clouds so that from a customer standpoint, the experience is seamless. There are three main areas that I want to call out. And then I'll talk about how we actually do it. One, we want to create the same cloud platform experience. Two, we want to map the resources to some native identifiers so that customers don't feel like they're actually using two different clouds with two different identifiers and implications of that. Three, we want to bring the virtual networking or the customer's private networking close together so that they feel like it's actually part of the same network. What does it mean? So let's actually first take a look at the identifiers. Well, let's start with identity system. OCI has a system called OCI IAM. Azure has Azure AD. Let's say a customer is primarily an Azure customer. They already have an Azure application running in Azure, and they have set up their Azure AD. They have users, passwords, and roles and groups and whatnot. And then now they actually want to launch Oracle Database Service for Azure. Now, the Oracle Database Service for Azure is actually a database instance or service that's actually inside OCI, and it actually uses OCI IAM. But we don't want to complicate the experience for the customer. So what we do is we actually map the Azure AD roles and groups to the corresponding roles and groups in IAM. And that way, when customers want to use Oracle, database service for Azure, all that they do is they go to Azure console, they look at, they log in using their regular user and password that's actually valid in their Azure AD, and they get to seamlessly operate the Oracle database resource, even though it's actually inside OCI, and the mapping between AD and IAM essentially takes care of it. Network connectivity. So again, we want to give customers a very smooth, seamless connectivity. So customers have an Azure application on the left running in Azure. They essentially have a VNet, which is a virtual network, and then it actually connects, and then they have an OCI database running in OCI, and they kind of want, they want to see the VNet and the VCN, which is essentially, OCI's virtual network, if you will, or private network, connected seamlessly. That should be the customer experience. That is our goal, right? But in order to do that, we actually had to do a whole bunch of, plumbing down the surface. We essentially built an underlying layer called multi-hub. This is not something that visible to customers, but this is internal implementation details, if you will. What we do is essentially use OCI Fast Connect and Azure Express Route to actually connect Azure and OCI, and then we actually create our own a VNet inside Azure. The VNet is owned by Oracle, but it's inside Azure. And then there's a peering relationship from that VNet to the customer's VNet. So when let's say the customer's application is trying to access OCI database, it comes through the customer's VNet on the left, comes through the hub and spoke VNet, goes through the express route to the Fast Connect, and then comes to our VCN and goes to the Oracle database. But none of this is visible to the customer. They just perceive as if their customer VNet is directly connected to OCI's customer VCN. And that's the seamless experience we're trying to give. Well, some of the other databases, there are multiple types of databases in OCI. ADB is Autonomous Database Service, and they actually have a special feature. They can actually project the endpoint of the database itself as a private IP in customers' virtual network. We've had that in OCI for a while, but as part of the Oracle Database Service in Azure, we actually wanted to give the same experience for Azure customers as well. So if you look at the left side, well, it's kind of similar to the previous one, except that we actually use the Azure Private Link mechanism to actually launch an ADB private IP inside the customer's VNet. So now customers, when customer applications, they just need to talk the private IP inside their VNet. The packets get routed through the private link, through the multi-cloud connectivity inside our multi-cloud hub that Oracle owns and built, all the way to the service gateway in OCI side, and then into the autonomous database, right? So this is a bunch of sausage making behind the scenes. But what it does is essentially provides a seamless experience for Azure customers when they want to access Oracle database. Similarly, let's say Azure customers have metrics and log dashboards, and they already set it up for a bunch of services. They want to use the same experience, the logging and the metrics, when they use Oracle database service in Azure as well. Well, in reality, the Oracle database is actually running in OCI. So by native means, they actually generate OCI metrics and logging. So we essentially, as part of the multi-cloud hub that OCI built, we essentially have adapter mechanisms wherein we can essentially take the Oracle database generated metrics and logs and convert them into Azure metrics and logs so that customers in Azure essentially see a seamless dashboard of metrics and logs. All right, cool. So takeaways. OCI has a fundamentally differentiated product strategy to address customer requirements. That includes having many small and large public regions as well as private regions, aka DRCCs. And we want to give customers a seamless multi-cloud access. None of that is possible unless we step back and look at the core architecture and actually make the right enhancement and investments into that. And that's exactly what we have been doing in OCI for the past few years. And that's exactly how we have been able to launch DRCC, have launched more 40 regions and more. And this is essentially foundational for delivering on our vision. Thank you.